Hello guys, welcome to this lesson. We will be looking at question 5 of our paper 2, which involves the proof of a theorem under Euclidean geometry. How does it look like? Take a look. Okay, we are given a diagram, as you can see on the board, and we are asked to prove that the opposite angles of a cyclic quad are supplementary. To be specific, we must prove that angle C plus angle E, is equal to 180 degrees. In all the grade 11 theorems, the construction that is involved there is mainly a radius, because then it allows us to talk about angle at center theorem, and also in theorem 1 and 2, where we have right angled triangles, can allow us to talk about theorem of Pythagoras and congruency of triangles. All right. So in this case, this is our construction. We're drawing DA and we're drawing AF. Okay. So as you can see, we have radius lines here. Angles at center equal to 2 times angle at circumference. And again, angle at center is equal to 2 times angle at circumference. So we're gonna link this angle to that one, and obviously this angle here will be linked to this one there, just to create distinguishing factors there. So that is our construction. So here's the proof. Okay, and I'm gonna call this A1 and A2. Angle A1 is equal to 2 times angle C, this is angle at center, equal to 2 times angle at circumference. Okay, what do we know about A2? Angle A2 is equal to 2 times angle E. Angle at center is equal to 2 times angle at circumference. Okay, but adding these two angles around a point, add up to 360. Okay, however, we know that angle A1 plus angle A2 is 360 degrees, so angles around a point. Okay, substitution takes place. Okay, and we divide both sides by 2. Therefore, angle C plus angle E is equal to 180 degrees, which is the end of our proof, showing that indeed when you add C and E, you get 180 degrees, and therefore they are supplementary angles. Right, so this takes care of question 5. Alright, so in this video we are asked to calculate the magnitude of angle E1. We're given 2 circles of different sizes and some angles here. We have 75 degrees at H and 73 degrees at D, and we are told that GE is actually a tangent to the smaller circle. Alright. So how can we go about doing that? Just following it up from our proof of the theorem, if that is 75 degrees, we know that opposite angles of a cyclic quad are supplementary. So 75 plus what here, which is E1 plus E2, it's a split angle there. E1 plus E2 will be equal to what? 180 degrees minus 75, which is 105 degrees, right? These are opposite angles of a cyclic quad. Okay, that is what we know. However, this angle 73 is subtended by this chord CE, yes. However, this chord CE makes contact with a tangent here. There's a tangent GE, right? So the angle between the tangent and the chord is equal to the angle subtended by the same chord at the circumference of the circle in the alternate segment. So what must this angle be? It must also be 73 degrees, which is actually E2. Okay, so E2 is equal to 73 degrees, and that gives us, that is from the 10 chord theorem. Okay, so substituting there, we know that E1 will be equal to 105 degrees minus 73 degrees, okay, giving us 32 degrees. And this takes care of this question. That was question B under question 5. All right, so let us move on to C. Here you go. Okay, so let us start with C1, where we are asked to find the magnitude of D2. Okay, first of all, let us just add some information here. A is the center, so that will make AD a radius, and AB also a radius, R. Okay, so what type of triangle is this? An isosceles triangle, and therefore the two angles B2 and angle D2 are equal. Okay, so we know that angle D2 will be equal to 180 degrees minus 86, giving us 94 degrees. We divide this by 2, and that will give us 47 degrees. Okay, 94 degrees divided by 2. So these are, this is angles opposite equal sides. Okay, so this takes care of C1. What about C2? We're asked to calculate angle DEB. So DEB is angle at the circumference. Is it associated to that? Yes, angle at center. Right, angle at center is equal to 2 times angle at circumference. So definitely angle DEB will be then 43 degrees. Angle at center is equal to 2 times angle at circumference. All right, good. So this takes care of the first 2 questions. Right, let us look at the last question. That is question C3. Here you go. Now we are asked to prove that DACB is a cyclic quad. Okay, already we have some angles to play with. However, knowing that F is a midpoint and A is the center of the circle, and line from center to midpoint of chord ED will make a 90-degree angle definitely right there at point F. Okay, so in this triangle, we have the 2 angles. We can work out C, okay? And whatever C is, okay, it becomes the exterior angle of this cyclic quad that we will prove in a moment, and we can associate it to that angle. And if that is 47, it would mean that definitely we have a cyclic quad there. All right, so therefore let us write it down or structure it correctly. Okay, so we can talk about AFD. Angle AFD is equal to 90 degrees. Line from center to midpoint of chord. Okay, and therefore C1 is equal to 180 degrees minus 90 minus 43, giving us 47 degrees. These are interior angles of a triangle, okay? But we know that angle D2 is equal to 47. What happened? This was proven in question C1. And therefore, C1 is equal to D2, which means that DACB is a cyclic quad because exterior angle is equal to interior opposite angle. All right. Alternatively, this reason can be written as converse of exterior angle of a cyclic quad. All right. So this takes care of question 5. And in the next video, definitely we'll be talking about question 6, which is about some statistics. All right. So yeah, let's be on the lookout for that. Thank you for tuning in. See you on the other side. Sharp.